Hi, everyone. Thank you for joining us today. My name is Adira, and I am one of your Solid State Circuit Society staff members. The topic of today's webinar is The End is Near, the problem of PLL power consumption, presented by Professor Behzad Razavi. Today's webinar will be a little over an hour. We will hold a Q&A session in the middle of the webinar for a few minutes, and then an extended Q&A session after Professor Razavi's presentation. Please use the Q&A section of your dashboard in WebEx to ask any questions. Attendees of this webinar will have the opportunity to earn a certificate of participation, and I'll post a link and details on how to obtain the certificate in the chat section. The webinar slides and video will both be posted on the SSCS Resource Center within a week free of charge. I now invite Alvin Loke, Chair of the SSCS Webinar Committee, to introduce our speaker and give a few welcoming remarks.
Hi, good morning, good afternoon, good evening, everyone. Welcome to this second Solid State Circuit Society webinar of 2021. Hope you and your family and your loved ones are staying safe and well. Today, we are absolutely delighted to have Professor Behzad Razavi presenting a webinar. So obviously, he needs absolutely no introduction whatsoever. But just briefly, he's a professor of electrical engineering at UCLA. Where he works in the areas of analog, mixed signal, and RF integrated circuits. He's an IEEE fellow. Obviously had all the important honors in our society. Distinguished lecturer. Published hundreds of papers, many books, translated many languages, and so forth. Basically his accomplishments are just simply second to none. But anyways, I'm sure you'd like to hear him talk more than me. So let's bring Professor Razavi on at this point. Professor Razavi, thank you so much for making time out of your crazy schedule to help us understand this problem of PLL power consumption, which many of us are facing as a very near and dear problem. Really appreciate your time. Thank you.
Thank you, Alvin, and good morning, good afternoon, and good evening to everyone. Today, I would like to talk about the trade-offs that we face in the design of phase lock loops in terms of jitter and power consumption. I will begin with some introductory remarks and show why we are going towards very small jitter values and what applications are imposing in terms of jitter. And then I will present the framework that I have used for my analysis and the assumptions that I have made to be able to derive some simple intuitive equations that predict the future trends. Then I will use this framework to obtain some lower power bounds for the power consumption of the PLL, and in particular the VCO, if we are to meet a certain jitter requirements. And then I'll extend this to the jitter power trade-offs for analog to digital converters, trying to see what jitter we can tolerate for a given S and R penalty in the A to D, and then eventually how much power consumption that translates to. And then finally, I will present some trends that seem quite prohibitive in terms of power consumption, and we'll talk about some mitigating factors that hopefully will ease these trade-offs and summarize with a conclusion. We have PLLs in various microelectronic systems. In wireline transceivers, we have a PLL on the transmit side. In this paper, they present a 128 gigabit per second PAM4 transceiver. This is the transmitter, and I have just drawn my own PLL here to indicate that there's a clock necessary for this transmitter. And then similarly, on the receive side, we have an analog digital converter that digitizes the received signal and further processes it. And that A to D also needs a PLL, and that PLL also has to have a sufficiently small jitter. In the wireless domain, we have similar challenges. Here's an example of a dual concurrent MIMO Wi-Fi system. And that means that there are, for example, two receivers operating at the same time. And that means there are two PLLs that are operating at the same time and must have a low jitter as well. So their power consumption becomes critical. In this example, we have 1024 QAM, and that requires a jitter of no more than about 70 femtoseconds RMS in the transmitter and in the receiver. Finally, we also have A2Ds, and here's an example from analog devices, a 12-bit A2D that operates up to 12 or 18 gigahertz. And we would think that the clock driving this A2D must also have sufficiently small jitter so as not to degrade the SNR significantly. So I would like you to remember this power consumption here for the case of 12 gigasamples per second for this A2D. And later on, as we look at the PLL that will provide this clock to the A2D and see how much power consumption it would need, it will be interesting to compare these two numbers. All right, so let's be a little more quantitative and see what kind of jitter values we might need in the near future. In wireline transceivers, we are looking forward to 224 gigabit per second transmitters and receivers, probably working with PAM4 signaling. And in that situation, the symbol period at the output is about 9 picoseconds. So that means that the jitter we can tolerate in the transmitter is about 100 femtoseconds RMS. That's okay. The frequency, of course, is very high, and the jitter is relatively low. On the receive side, we are using a 7-bit A2D to digitize this PAM4 signal. And for that A2D to not degrade its SNR due to clock jitter, the clock jitter has to be less than 10 femtoseconds. In the wireless domain, as we just saw, for Wi-Fi 6 with 1024 QAM, we need a jitter on the order of 70 femtoseconds RMS. And in 5G applications around 30 gigahertz, if we do use 256 QAM, my estimate is that the jitter should be about 20 femtoseconds. And then finally, in Wi-Fi 7, which is upcoming, and we are going to 4096 QAM, the jitter also has to be less than 20 femtoseconds. And finally, for example, for the 12-bit 12 gig ADC from analog devices, the jitter has to be less than 10 femtoseconds. So we see a great need for low jitter values in these applications that are forthcoming. And we have to see what it takes, how much power consumption we need to approach these jitter levels. Okay, let's start with a very simple integer NPLL consisting of a phase frequency detector, a charge pump, a low-pass filter, a VCO, and a feedback divider. And we know that this VCO contributes phase noise at the output of this form. We start out with the free-running phase noise profile here, and then upon phase locking, we shape it into something approximately looking like this, where we have a plateau between minus F2 and plus F2, and then a decline on the two sides. In addition, we have reference phase noise, and that also propagates to the output according to the transfer function of the PLL. So that experiences a low-pass action and comes out in this form. And in this flat region, the phase noise of the reference is multiplied by n squared. So we have to look at these jitter contributions and see how much power this VCO needs to spend at minimum to be able to meet a certain jitter requirement. So I'm making some assumptions. Here are the assumptions. So I'm assuming that this VCO phase noise is flat from minus F2 to plus F2. And I'm assuming that the transfer function from here to here, as far as the reference phase noise is concerned, is a first order low pass filter. And finally, assuming that F2 and F1 are approximately equal. And these conditions hold typically if the damping factor of the loop is approximately 2 or higher. Also, as an optimistic estimate, I'm neglecting spurs, the VCO flicker noise, the PFD noise, the divider noise, and the low-pass filter noise. So ultimately, we're just looking at the VCO phase noise, the input phase noise, and just a few words about the charge pump, and maybe a few words about the divider. So our objective is to find the minimum power consumption that this VCO needs in 3 cases. Case number 1, only the VCO has noise contribution. Case number 2, the VCO and the reference have noise contributions. And case number 3, the VCO, the reference, and the charge pump have phase noise contributions. And we would like to see how much power the VCO has to burn. All right, so let's start with case number 1. Only the VCO has phase noise, and see what power consumption is necessary. Because we are neglecting flicker noise in the VCO, we can express the free-running phase noise of the VCO as alpha over f squared. F is the frequency offset, and alpha is a factor that depends on the oscillator topology and its power consumption. And when the VCO is phase locked, we have this shaped phase noise profile. So we have to integrate this area to find the total jitter. And when we integrate that area, we end up with 4S1 F2. F2 is the loop bandwidth, and S1 is the phase noise of the free-running oscillator at the frequency of F2, where this profile and this profile meet. All right, so this area is in radians, radians squared. So we want to convert this to seconds squared, and that means that you just have to normalize it to the clock period. So we obtain this equation for the jitter contribution of the VCO while it is phase locked. All right, so that's easy enough. The only unknown here is S1. S1 is the phase noise of the free-running oscillator at this offset, and it depends on the type of oscillator that we have. So let's pick an oscillator, our standard LC topology, and let's assume that we have only white noise from M1, M2, and the tanks, and no noise from the tail current, and no flicker noise. So under these conditions, we can derive an expression for the phase noise given in this paper. And now I'm going to make one more assumption. The assumption is that the single-ended peak-to-peak swings at X and Y are approximately VDD over 2. Well, if you make that assumption, then we can replace for RSS RP in this equation in terms of the power consumption of the VCO, which is given by ISS times VDD, and that readily gives us this equation. So this equation is the phase noise of this particular oscillator as it trades with its power consumption, and then some basic constants that we have. Okay, now that I have the phase noise equation for this oscillator, I can compute it at an offset of F2. So I just replace this F, frequency offset, with F2, and that gives me S1, and then I take this S1 to here and replace it here. And from there, we can find a simple equation for the jitter of the VCO and how it trades with the power consumption of the VCO. Okay, so we are really interested in the power consumption, so let's just swap these two here and end up with this simple expression. This is the minimum power consumption necessary for the VCO to be able to give us an integrated jitter of sigma j, while the loop bandwidth is equal to F2. The Q is just the Q of the tank, and we'll have to see how that plays in our design. So let's eyeball this result a little more and look at some of these attributes. What we see is first, the power consumption of the VCO is actually relatively independent of the output frequency. There is some dependence only through Q, because the Q of the tank depends on the oscillation frequency and how we design it. But beyond that, there's not much dependence on the output frequency of the circuit. Now, how serious is this trade-off? So let's look at some numbers just to get a feel for the situation. I will make some assumptions We'll assume that Q is 10 for the tank. Gamma, the noise coefficient of MOSFETs, is 1. And the reference frequency is 100 megahertz. And I'm considering in two cases, a loop bandwidth of 10 megahertz or 5 megahertz, depending on how we are designing our PLL. So we have here the power consumption of the VCO as a function of the required jitter. And we see that, for example, if the jitter is to be 10 femtoseconds RMS, and the bandwidth of the loop is 10 megahertz, the power consumption is 28 milliwatts. If we cannot live with 10 megahertz and we have to reduce the loop bandwidth to 5 megahertz, then of course the power consumption goes up by a factor of 2. So I would like you to remember this example, 28 milliwatts for 10 femtoseconds of RMS, and we will soon see that the situation actually becomes much worse very quickly when we go to case number 2. So in case number 2, we have the VCO phase noise contribution and the PLL and the reference phase noise contribution. Okay, so we have to add up these two areas, which I call the area of under the reference contribution and oscillator contribution. And we know that there should be some optimum here. For example, if I just reduce the loop bandwidth by a factor of 2, the reference contribution goes down, but the VCO contribution goes up because its phase noise is corrected to a lesser extent by the loop. So what we have to do is add up these two areas and then figure out under what condition they reach a minimum. So I will call these area ref and area VCO. So let's go ahead and do that. Area ref can be obtained if we have the shape of the spectrum, and the shape of the spectrum is the reference spectrum, which I assume to be flat, multiplied by the squared magnitude of the transfer function from here to here. So if I assume that the transfer function is of first order, then the output spectrum resulting from the reference is given by this expression. So we go ahead and integrate this from minus infinity to plus infinity, and that will give us the area ref, which is given by this expression. Okay, we already found area VCO to be 4S1 F2, and we know that S1 here is the intersection of alpha over F squared and this flat profile, so it's computed at F2. And we also assume that F1 and F2 are approximately equal. So now I can just add up these two expressions with these substitutions and differentiate with respect to F2 or F1 to find the minimum value of this area. So we do that, it's not that hard, and we obtain the optimal bandwidth to be this expression here. Okay, so what we see here is that the minimum total jitter at the output is given by this expression. And everything here is known except for alpha. Again, alpha depends on the design of the oscillator, as we saw here in this profile. But when we reach this optimum, the contributions of the VCO and the reference are approximately equal. So we just need to replace for this alpha so that we have a simple equation for a given oscillator design and PLL design. So let's go ahead and do that. I have this expression, and I just need to find alpha. Okay, so we go back to our basic oscillator and remember this equation that we derived before. Because we are looking for an expression of the form alpha over F squared, everything in this equation except for F squared becomes alpha. So we just take this and replace it here so that we can find the total minimum integrated jitter at the output of the PLL resulting from the VCO and the reference. And that brings us to this equation. This equation will play a critical role in everything that follows from now on in this presentation, and it will show some alarming trends in the power consumption and jitter trade-offs that we face in the future. Okay, so a few observations. Number one, this equation is valid for subsampling PLLs as well, simply because any PLL has to deal with the VCO phase noise and the reference phase noise. Those are inevitable. We also see that the power consumption necessary for the VCO now is proportional to the inverse fourth power of the required jitter. So if I have to reduce the jitter by a factor of 2, I need to increase the power consumption of the VCO by a factor of 16. And again, this PVCO is relatively independent of the output frequency or oscillation frequency, except for the dependence of Q upon that frequency. And finally, we see that if we want to reduce the power consumption of the VCO, we can try to increase the reference frequency, but only if the reference phase noise doesn't go up proportionally. So in other words, we should be looking for a crystal oscillator for the reference of the PLL such that SREF over FREF squared for that crystal oscillator is minimum. And that depends on the design of the crystal oscillator, its frequency, and other parameters. Okay, so now that we have derived this equation, we can go back to our example of 10 femtoseconds of jitter and see what it takes now that we have included the reference phase noise, namely case number 2. So again, remember that I assumed the Q of 10 for the tank and the reference frequency 100 megahertz. So if the reference has no phase noise, we saw before that the power consumption was 26 milliwatts. Okay. But now let's assume that reference has phase noise, for example, minus 170 dBc per hertz. And that now gives us a power consumption of 840 milliwatts for the VCO. So this number is shocking, but let's try to see how this happened. Why was it that we had 26 milliwatts without reference phase noise, and suddenly now we go to 840 milliwatts if the reference phase noise is included? Well, the ratio from here to here is about a factor of 32. So how does that happen? Well, remember that if we include the reference phase noise, now we have to reduce the loop bandwidth and reach that optimum value where the VCO and the reference contribute approximately equally. So when we do that for this particular example, we see that the loop bandwidth is no longer that 10 megahertz I had assumed before, but now it's only 630 kilohertz. So we have a factor of 16 reduction in the bandwidth of the PLL. And that means that the VCO phase noise contribution goes up significantly. And to make up for that, I have to increase the power consumption of the VCO. Remember that PVCO is inversely proportional to the loop bandwidth. So if the loop bandwidth goes down by a factor of 16, this has to be multiplied by a factor of 16 so that sigma j doesn't change. So for a given jitter contribution, the VCO power consumption has to go up by a factor of 16. But there's yet one more consideration. Now we have both the VCO and the reference contributing phase noise. So each of them has to contribute half as much as before. So there's another factor of 2 that we have to include. And that's why we end up with a factor of 32 increase in the power consumption of the VCO. Okay, so this is what it takes to provide a jitter of 10 femtoseconds RMS at the output of the PLL if we have these assumptions: Q is equal to 10, the reference frequency is 100 megahertz, reference phase noise is minus 170. And of course, a power consumption of 840 milliwatts is ridiculous in many dimensions. For example, if you were to design the circuit for a power consumption of 840 milliwatts, exactly how would that work, right? We end up with 840 milliamps of tail current, a device width on the order of some millimeters, inductance values in the range of picohenries. The numbers would just not be practical. So that poses many interesting challenges. Okay, so Let's plot this result that we obtained. Again, the power consumption of the VCO as a function of the jitter that we require, and see what numbers we end up with. Again, I'm assuming the reference is 100 megahertz and the phase noise is minus 170. And I'm considering two cases for the reference frequency of 100 megahertz or 50 megahertz, depending on what we have. Okay, well, I should explain a little bit about the trends down here at higher jitter values, let's say some near 100 femtoseconds. Around here, the optimum bandwidth that we obtained before actually exceeds 1/10 of the reference frequency. So I have deliberately limited the loop bandwidth to 1/10 of reference frequency around here. And that's why you see a little kink in these plots. But let's go back to the familiar territory of 10 femtoseconds. We saw that we had 840 milliwatts of power necessary for the case of 100 megahertz reference frequency. And if the reference frequency goes down by a factor of 2, the power consumption has to go up by a factor of 4. So now we're in the watts range. So that is quite discouraging. And there we look at 5 femtoseconds. Well, at 5 femtoseconds RMS, now we're dealing with some 10 watts or some tens of watts for the power consumption of the VCO. And then what happens if we go to 1 femtosecond? Way out here. Here we're dealing with some tens of kilowatts of power consumption. Okay, that's what these results predict. Let's hope that these results don't hold in the future, otherwise we will be out of jobs. All right, now let's switch gears to the charge pump noise. Again, it depends on the type of phase lock loop that we have. For example, if we have subsampling PLLs, all the mechanisms I have presented so far apply, but we don't have a charge pump necessarily, so the charge pump phase noise may not be present there. Nevertheless, if we do have a charge pump, the question is its phase noise contribution a serious problem or not? So we just want to get a feel for that. All right, we know that the current sources in the charge pump carry a certain amount of noise current, which I have denoted here by IN. And what we see is that this current is switched periodically as it appears at the output of the charge pump. So the current is injected for some amount, which I call TCP, and then it's not injected. This TCP is the pulse width of the up and down pulses that we have at the output of the PFD. And it's typically about 5 gate delays if the PFD uses basic NOR-based or NAND-based topologies. So what we can do is, if we assume only white noise in this current source, we can see that the white noise is switched periodically. And when that happens, the result's still white. So we can transform that circuit to this circuit where we have an equivalent white noise current source continuously injected to the output node. The difference is that the spectrum of this new current source is scaled, from this one by a factor equal to the duty cycle of the switching actions. So essentially is multiplied by TCP over Tref. And then we refer this result back to the input of the PFD to obtain this spectrum. So this is the noise spectrum created by the noise in the charge pump when it is referred to the input. And as soon as it's referred to the input, it becomes indistinguishable from the reference phase noise. So now we can just go back to our equations, and if we have SREF, the reference phase noise, we can simply add this to it, and this is the result that we get. Okay, so we see that the charge pump phase noise, when referred to the input, is as serious as the reference phase noise. And the question is, what does it take for the charge pump phase noise to be perhaps negligible with respect to reference phase noise? So let's look at some numbers and see. Okay, suppose that I would like the charge pump contribution to be just equal to the reference phase noise. That's not very desirable, but let's just do that. So our reference phase noise has been minus 170 dBc per hertz. So we can equate the charge pump contribution to minus 170. And then for the noise current produced by the transistors in the charge pump, we can express that in terms of their overdrive voltage and so on, and their bias current. And then we also make a few assumptions. We assume that we have 5-gate delays for TCP. That's about 50 picoseconds. We assume an overdrive voltage of 100 millivolts for the transistors in the charge pump, the current sources. And the result is that the charge pump current has to be 13 milliamps. So this requires extremely large devices in the charge pump with lots of capacitances and lots of delays. We have to be able to turn these transistors on and off in 50 picoseconds. So that becomes a great challenge just in terms of charge pump design. The power consumption of the charge pump is not that high because this 13 milliamps appears only for 50 picoseconds out of, for example, 10 nanoseconds. So it's negligible. But we still have 13 milliamps that we have to deal with. And even in this situation, because these two contributions are equal, the necessary power consumption of VCO still has to double. So all of the numbers I presented before now have to double, even if we design the charge pump to have a phase noise of minus 170 dBc per hertz. So that continues to deteriorate the situation. So in summary, this is what we have observed. For a jitter of 10 femtoseconds, when we had only the VCO contributing, we had a power consumption of 26 milliwatts. That was okay. But then once we included the reference, we went up to 840 milliwatts. And now that we include the charge pump, we can go up to about 1.7 watts. Okay, I think we are halfway through. Maybe I will pause and see if there are any questions before we continue.
So several questions. So one person comments is there any reference oscillator known that combines the values of minus 170 dBc per hertz at 100 megahertz offset? He has never seen such a device.
Yes, I will show an example very shortly. Yes. Okay.
Next question. 4 gigabit per second PAM4 receiver. What are the assumptions for the link operating bit and forward error correction? Would it be fair to look into trading off PLL power for FEC power?
Right. Yes, I did not make assumptions about those aspects of the design. So the way I looked at it was that we have a symbol period of 9 picoseconds at the output of the transmitter, and we want the jitter of the clock to be sufficiently small. If we assume that the jitter is 100 femtoseconds RMS, then its peak to peak is about plus minus 400 femtoseconds. And that's roughly what we would expect to hold for proper detection of the signal later. I understand that when this signal is received by the receiver, the clock and data recovery loop will eliminate some of the low frequency jitter. So yes, that 100 femtoseconds is probably pessimistic. We can tolerate more. Now for the receive side, I'm assuming that we have a 7-bit A to D running at 112 gigasamples per second. And we want the SNR of that A to D to be degraded by only some amount. And the next part of this presentation, I will quantify that and I will show you how we can obtain the minimum or the maximum tolerable jitter if we have a certain SNR penalty for the A to D.
Okay, that seems reasonable. On page 7, what is the assumption, under what assumption that VCO noise, give me a second, sorry, at the output is flat between plus or minus F2? If filter is used, will VCO noise at the output look more like a bandpass instead of flat?
Right, yes. So, right, so let me go back to one of these profiles. that we had here. Yes, so whether this is really a flat here or not is depends on the type of the PLL. Typically what happens is that the other sources that they have neglected tend to fill up any hole that we have here, even though this might be a bandpass function. So for example, the noise of this low pass filter, whatever it is, will contribute in this vicinity as well. So in practice, it is actually difficult to see a noise profile for the output of the PLL that really shows that bandpass behavior that the theory predicts. Yes, for the VCO itself, it would be a sort of a bandpass spectrum, but given these other imperfections that I have neglected, it would eventually turn out to be relatively flat.
Got it. Next question. There are lots coming in. I don't think we're going to be able to get the, but for the last example, would it make sense to increase pump current and make its contribution to the jitter more negligible? This is referring to the charge pump.
Yes. Well, we could, but the question is how far can we go? So 13 milliamps is a lot of current. Think about the supply transient current that we produce in situations like this. So this charge pump turns on and draws 13 milliamps from the supply. So we have to bypass the supply really well. That takes very large capacitors. And if we wanted to make it negligible, we could try to do that, but how much current do we need? So let's say I want to go, I don't know, 6 dB below this. So for 6 dB here, I would need to increase the charge pump current by a factor of 2, right, by a factor of 2. So that means it would be 26 milliamps. So yeah, so these are basic equations, and depending on how aggressive and ambitious we are, we could try to design this for even higher current level. But the problem is that if the charge pump is to deliver, let's say, 26 milliamps, then these transistors have to be extremely large. And if they are very large, this PFD now has to drive a very large capacitance and yet turn the switch on and off in 50 picoseconds. So that translates to designing a very large PFD, and it just propagates backward and causes other issues.
Got it. Another question, does going to the an all-digital PLL topology off better?
Well, as far as the VCO power consumption and the reference power are concerned, no, the reference phase noise. So this part of the equation is not there for a digital PLL because we don't have a charge pump, but this part is here. So again, the result that I obtained before, which is more general, this result applies to all PLLs. It doesn't matter what type of PLL we have. Of course, in digital PLLs, we now have other contributions by the TDC and by the quantization noise of the VCO, etc. But this is sort of the bare minimum power that we would need, regardless of the type of the PLL.
Got it. Question before we move on. Obviously, there's a lot of interest. You made the assumption F1 and F2 are the same to solve for an bandwidth. What if they're different?
Right. So then we have to, right. So what happens in that case is that these two area equations will not be the same. So there will be F1 and F2, and F1 and F2 will be related still. For a given PLL, F1 and F2 are related. We have equations for them in terms of the damping factor and the natural frequency, etc. So we can use those equations if we so desire. And there's always a little more complicated. We can still find the optimum, but this helped me create a very simple scenario. And also keep in mind that as we see, the loop bandwidths are going down in the situation. And to reduce the loop bandwidth, we inevitably end up using a large damping factor for the loop. And when we use a large damping factor for the loop, F1 and F2 will be close to each other. There's not much difference between them.
Got it. Okay. Well, thank you, Behzad. In the interest of time, can you let's continue with the presentation. We'll take more questions towards the end.
All right. Very well. Let's continue. Okay. All right, so we talked about this situation and the effect of charge pump. All right, so the analysis of phase noise in frequency dividers is beyond the scope of this presentation, but I thought I'd just mention a few words about their contribution to the output phase noise. So here's a divider, and I have modeled this phase noise by this additive term at the output. What we see is that this phase noise goes back to the input, and in a sense, it becomes indistinguishable from the reference phase noise. So we can say that the divider phase noise experiences the same transfer function as the reference phase noise. So if we want the divider to have negligible contribution, its phase noise must be well below the reference phase noise. So that's a simple guideline that we can use and judge whether the divider is good enough or not. Now, we can go back to prior work and see some of the work, some of the results that people have obtained. In this paper, they have this dual modulus divider that divides from 3 gigahertz to 70 megahertz, and they use a retiming flip-flop. And with the retiming flip-flop, they obtain a very low phase noise. You can see that they get about minus 172 dBc per hertz. So that's pretty good. It's still close to the reference phase noise of minus 170 that we assumed, but it shows some promise that using a retiming flip-flop can essentially remove the phase noise of everything else, and essentially we end up with only the phase noise of a single flip-flop. So to explore that a little more, I designed a little retiming flip-flop myself, as shown here. And I'm assuming that I have a clock at 20 gigahertz coming from the VCO, and the reference, the feedback signal from the device is flowing this way, and that signal is at 100 megahertz, as we have assumed so far. So we are retiming a 100 megahertz signal using a 20 gigahertz clock by means of this flip-flop. And now we want to see what we obtain for the phase noise. So here are the results in this 28 nanometer technology. If we go with the device dimensions that I have shown here, that would be our original design, and it consumes 0.6 milliwatts, mostly in the clock path. And the jitter integrated from 1 kilohertz to 1 megahertz is about 5.4 femtoseconds. I integrate only up to 1 megahertz because remember that the loop bandwidths we are dealing with now are falling below 1 megahertz anyway. And if we so desire, we can go and scale all of these widths up by a factor of 2 for a power consumption of 1.2 milliwatts. And then if we integrate this, it's about 3.5 femtoseconds. So the point of this exercise is that if we use retimers in our feedback dividers, then the jitter power trade-off that they impose is far more relaxed than what we see for the VCOs. Okay, switching gears to the jitter in A to D converters. So we have found general equations that allow us to find the trade-off between the power consumption of the VCO and a certain desired jitter. So now when it comes to A to Ds, we have to ask how much jitter is tolerable, and then how much power do we need to consume in the VCO, in the PLL that drives that A to D. Okay, throughout this analysis, I will refer to this example from ISSC 19, a 12-bit 5 gigahertz, 159 milliwatt A to D. I would like you to remember this power consumption, and then we'll see how much power consumption the VCO or the PLL will need to drive this A to D. All right, so here's the situation. We have a simple abstract view of the A to D consisting of a sampler and the quantizer. I'm assuming that the resolution is m bits, and this clock is coming from source of the PLL. And in the ideal world, the clock has no jitter, so we are sampling these points uniformly, and the SNR of the overall A to D is given by the signal power over the quantization noise power. So that's easy enough. In reality, the clock has jitter, so these points move around randomly, and they introduce noise in the digitized signal or in the sample signal. So to quantify the SNR of the A to D in this case, we have to go and add a certain jitter-induced power to the quantization noise power in the denominator of the SNR. And if the input is a sinusoid at the frequency of Fin, then this jitter-induced noise power is given by this expression. Okay, so now that we have this, we can decide how much SNR penalty the A to D should take for jitter. So we have to quantify that. Are we willing to have a 1 dB of penalty, 2 dB of penalty, or more? And based on that, we can decide how much jitter we can tolerate. So let's quantify that. The SNR penalty will be defined as the ideal SNR divided by this real SNR. And we want that to be some amount. So we want, we want to have lowercase m dB of SNR penalty. So if we decide on how much little m should be, that gives us an equation in terms of the maximum tolerable jitter that the clock driving the A to D can contain. Here I've assumed that we are running at Nyquist. Okay, so now we have an equation for the amount of jitter that the A to D can take if it has capital M bits of resolution and it can tolerate lowercase m dB of jitter, of SNR penalty. So we have this equation, and we already found the trade-off between the power consumption and jitter of the PLL. So that was this equation. Okay, so before we go there, I just wanted to mention a few things. Let's try to quantify how much jitter is necessary for different types of resolutions and for different amounts of SNR penalty. So here I have plotted the tolerable jitter as a function of the resolution for 1, 2, or 3 dB of SNR penalty. I'm assuming that the clock frequency, the sampling rate, is 10 gigahertz. So we see that as we go towards, for example, 12 bits, if you want to have only 1 dB of SNR penalty, then the jitter is below 10 femtoseconds. If you want to have 1 dB of SNR penalty, the jitter is about 3.2 femtoseconds. If you are willing to take 3 dB of penalty, the jitter is about 6 point some femtoseconds. And again, if you go back to that example I showed you before, if we want to design a 12-bit 5 gigahertz ADC, and we want to tolerate no more than 3 dB of SNR penalty from jitter, then the tolerable jitter will be 12.8 femtoseconds. Okay, so this gives us a feel for what kind of jitter values these A to Ds require. And now we can go and calculate the power consumption necessary for that. So this is the general result we obtained before. Now, if you don't have a charge pump, you can just drop this and just focus on the reference phase noise. And the result looks like this. This is the tolerable jitter we just obtained for the A to D with a resolution of m bits and an SNR penalty of m dB. So all I need to do is replace this whole thing for the sigma j here, and I will have a simple equation for PVCO versus the A to D parameters. And that gives me this equation. So in summary, this equation gives us the minimum necessary power consumption of the VCO if we drive an A to D with a resolution of capital M bits running at a clock frequency of FCK with a PLL reference frequency of FREF, and we wish to have only m dB of penalty in the SNR of the A to D as a result of the clock jitter. So going back to our 12-bit 5 gigahertz example, we say, okay, how much power consumption do we need if we would like to have 3 dB of penalty in the SNR of this 12-bit A2D. So with the same assumptions as before, Q of the oscillator is 10, reference is 100 megahertz, SREF is minus 170. I'm assuming the charge pump has no noise, so we can drop this term here, and the penalty is 3 dB. That will give us a power consumption of 330 milliwatts. So we see that the power consumption necessary for the VCO very quickly becomes comparable to or exceeds the power consumption of the A2D itself. And 3 dB penalty is a reasonable value to assume for the degradation due to the clock jitter. Okay, so if we look at this equation, it does predict certain trends that will become prohibitive in the near future. Number one, we see that PVCO grows with 2 to the power of 4m. So it's 2 to the power of 4 times the resolution, whereas for A2Ds, typically the power consumption is proportional to the m if it's just quantization noise limited, or 2 to the power of 2m if it's thermal noise limited. So we see that the power consumption of the VCO grows much more rapidly with m than the power consumption of the A2D. Similarly, we see that PVCO is now proportional to FCK to the power of 4, whereas for A2Ds, typically the power consumption is proportional to the clock frequency. So again, the growth of this power is much sharper with the clock frequency for the VCO than it is for the A2D. So here are some examples of how we end up reducing the PLL bandwidth when we are trying to achieve a certain SNR penalty and for a certain resolution. So here I have plotted the maximum allowable PLL bandwidth as a function of the resolution of the A2D. Remember, we have to do an optimization for the bandwidth PLL in terms of the reference phase noise and the VCO phase noise. So we see that the bandwidth down here in this down corner here drops below 1 megahertz. And also up here, things are more relaxed, so I have limited the bandwidth to FREF over 10. But here we are following the basic trend that we have. Okay, and then we can also look at the necessary VCO power consumption. Again, here I'm plotting the VCO power consumption as a function of the A2D resolution for different SNR penalties, assuming that the A2D runs at 10 gigahertz, the reference is at 100 megahertz, and the phase noise is minus 170. Again, around here, the situation is more relaxed, and I'm assuming that the loop bandwidth is limited to FREF over 10. If you look up here, the situation is quite serious. So if I have a 12-bit A2D running at 10 gigahertz, and I would like to have only 1 dB of SNR penalty from the clock jitter, then I need 77 watts of power dissipated in the VCO. All right, so that's no good. How about 3 dB penalty? With 3 dB penalty, I need to consume 5.2 watts of power in the VCO. So again, the situation is still rather bleak. Okay. Now, not everything is doom and gloom. There are some mitigating factors that will ease some of these trade-offs that I have shown so far. So if you relate to the VCO itself, I have assumed that the single-ended peak-to-peak swing here is VDD over 2, but we could design this VCO such that this peak-to-peak is about VDD. Of course, if we do that, then the flicker noise of M1 and M2 is up-converted, so we have to take other precautions to minimize that effect. But we can also try to raise the Q of the tank. I've assumed a Q of 10, maybe a Q of 15 is possible or higher. So that's a good effort to make. And also, this simple oscillator topology is not necessarily the best in terms of figure of merit. We can look at class C, class D, or class F topologies. that have better figures of merit and hence better trade-offs between the power consumption and their phase noise. So those can ameliorate the situation. Now, how about the reference, the crystal oscillator itself? Well, we can try to choose a higher frequency, but again, what we are really looking for is for SREF over FREF squared to be minimized. It's not just by increasing FREF. So we have to look at different crystal oscillators and see which one exhibits the lowest value for this ratio. And can we buy a crystal oscillator that has a phase noise lower than minus 170 dBc per hertz? Yes, so here's one you can buy from Vectron. This 100 megahertz crystal oscillator provides a phase noise of minus 178 dBc per hertz at 100 kilohertz offset. So that's encouraging. It improves our situation dramatically. But then the problem is that this crystal oscillator consumes 1.8 watts. So again, becomes an optimization problem. The crystal oscillator consumes a lot of power, primarily because at these phase noise levels, it's really the output buffer of the VCO, the crystal oscillator, that limits the phase noise, not the crystal oscillator itself. So they have to burn a significant amount of power in the output buffer. And it becomes a trade-off between the crystal oscillator phase noise and power consumption, and the PLL power consumption, and the A to D power consumption. One more mitigating factor is the following. When I analyzed the effect of jitter on the A to D, and I mentioned a jitter-induced noise power here, this assumes that we have a sinusoid at the Nyquist coming to the A to D. In practice, that's not the case. In practice, our signal actually occupies a broad bandwidth all the way to Nyquist. And it turns out that, according to this paper, if we have a flat spectrum from minus FCK over 2 to plus FCK over 2, this jitter-induced noise power actually is divided by 3. So that also helps in terms of the amount of SNR degradation that we can tolerate as a result of clock jitter. In summary, we have observed that the power consumption of VCO has this basic relationship to some simple values that we have and the amount of jitter that we would like to achieve. And then for A to Ds, we can use this result to obtain the minimum power consumption necessary if we have an M-bit A to D and we would like to have only M dB of SNR penalty in it. And these results indicate that the power consumption of BCO grows dramatically as we go to jitter values of some tens of femtoseconds or lower. And of course, we have neglected the PFD. Even if we neglect the PFD, charge bomb, divider, and low-pass filter phase noise contributions, we still see that we have significant power consumption requirements for jitters, let's say, around 10 femtoseconds. I hope you have enjoyed this presentation. Thank you for your attention.
Well, Behzad, thank you so much. Wonderful. There's a lot of questions I guess we'll get to. So thanks for preparing yourself with the drink of water. One question, actually several questions. So one is, do you see any difference between whether you have a Nyquist rate versus oversampled, for instance, like a delta sigma ADCs in terms of jitter tolerance?
Good question. Yes. I don't think there's much difference. So what happens is that in the case of oversampling, we are taking a bunch of samples and in a sense averaging them. So we have some jitter averaging in that respect, but that's really equivalent to having designed a phase lock loop with a lower clock frequency, proportionally lower clock frequency. So in other words, the nominal, the effective sampling rate. So I haven't analyzed that situation carefully, but my intuition is that there's not much difference between the two.
Okay, and so to a related question, in these PAM4 high data rate SerDes, obviously interleaving. So really, from your perspective, you don't really see the PLL power necessarily going down because essentially you still need accurate phases, right?
That is true. That is true. So if you are looking at the jitter contributed by the VCO, if you remember, it was not even much dependent on the output frequency anyway. So whether we have a low frequency VCO with multiple phases driving an interleaved A2D, or just a single high rate VCO driving a single channel, there's not much difference in the trade-offs that we face here.
Got it. Another question, do you have Vectron stock?
No, I don't.
The question, oscillator that you presented with the 178 dBc per hertz phase noise shows that, you know, I mean, these usually run at high voltages like 5 volts and 10 volts, but when it comes to CMOS operating 1 volt, the phase noise at minus 170 would go higher. Can you comment on this?
Yes, absolutely. Yes, I agree. I agree. So if you look at the integrated crystal oscillators that have been reported in the literature using CMOS technology in our domain, their phase noise is quite higher. They are on the order of minus 158 dBc per hertz at, for example, maybe 80 megahertz or 70 megahertz or so. So my objective here was to still have an optimistic estimate of the reference phase noise. If the reference phase noise is even higher, so let's say minus 160, then you can imagine how these power numbers will balloon into something completely unimaginable. So the point here is that we do need to design crystal oscillators with phase noise numbers down in the minus 170 range. If we don't, we are in deeper trouble than what I have portrayed here. So that calls for innovations in crystal oscillator design, PLL design, and even maybe jitter-tolerant A2D design before we reach these serious limits.
Got it. Do you see, along the lines of these references, do you see surface acoustic wave-based oscillators becoming prevalent?
Yes, so if we go to higher reference frequencies, we have two options. Either we can run crystals at their overtones, or we can go to SAW devices or other resonators. It's not clear to me if SAW resonators have any advantage or disadvantage with respect to overtone crystal oscillators. I haven't looked at the exact numbers. But also, again, we have to remember that we are looking for a minimum S ref over FREF squared. So by just looking for higher reference frequencies, we don't necessarily solve our problem. But certainly, those all should be considered.
So another question. Have you studied how different system architectures might mitigate the need low phase noise, such as multi-tone approaches for wireline or multi-band ADC architectures?
Yes, good question. So in terms of multi-tone signaling, actually one of my students published a paper many years ago, and it turned out to be actually more serious in terms of phase noise requirements because we have multiple narrowband spectra next to each other in the case of multi-tone signaling, and then if there's any overlap between them, that causes problems. So I haven't quantified these effects recently to see, in view of the very low jitter values that we need, whether, for example, multi-tone signaling would be better or not. Similarly, for A2Ds, if we go with multi-band quantization, rather than straight Nyquist digitization. I have a feeling that doesn't make much difference, but again, I haven't studied that.
Okay, next question. On the subject of supply noise, seems like the analysis does not really include supply noise. You know, what's your take on its impact and the relevance to perhaps using all digital architectures to mitigate some of that?
Yes. So if you go back to this diagram here, where we had various, okay, so in this diagram, we have various sources of noise, supply noise on this part of circuit, this part of circuit, and so on. So the supply noise will only make matters worse. Again, my objective has been to try to find an optimistic estimate for the lower bounds of power consumption of the VCO. So of course, if you have supply noise, and if you're looking for some tens of femtoseconds of jitter, the situation can be very serious. And again, I'm not sure what you mean by all digital architectures, but again, a digital PLL still exhibits the same exact trade-offs that I have shown before, given, for example, by this expression here, except that we don't have a charge pump. So if you just not worry about this, the main trade-off is still there. So that doesn't really solve this problem. Yes, the digital PLL may have less susceptibility to supply noise in some parts of it, but as far as the VCO design is concerned, it's still the same thing as an analog PLL.
Got it. Okay. And I guess a couple more questions. So one question, technology. So as we're moving towards these technology nodes, we have 5 nanometer products already in production. Clearly, there's the phase noise, the flicker noise contribution is soaring to the roof. I mean, we're seeing for the very small devices, corner frequencies into the gigahertz range already, right? So, factoring that in, how do you see, these trends play out?
Yes, very good question. Okay, so right. So again, the situation will be worse. So what happens now is that if we go back to some of these profiles that I use as an example, let's see here. So we will have some phase flicker noise from the VCO. There have been some recent examples. I think there was a class F oscillator reported a few years ago that does have a very low corner frequency for its flicker noise, down in the range of tens of kilohertz. So that's very impressive, and certainly it would be a good candidate for what we're doing here. So, but in any case, that will only raise this part of the spectrum if we have significant flicker noise up conversion from the VCO. And yes, the situation will be worse. So the contribution that we have here, namely 4S1, F2, will no longer be this value, it will be higher. So all of these really call for new circuit ideas, new architectures that can deal with flicker noise.
And to on technology, what about non-CMOS based solutions? Is that the way of the future? Obviously, there's a lot of excitement or attention paid to heterogeneous integration. Do we expect that people are going to be looking at those types of packaging technologies as a new space to solve many of these problems?
Yeah, yes, good question. Well, if heterogeneous integration allows us to increase the Q of the tank, certainly that helped because we see that it appears in all of our equations. So I'm not sure how feasible that is, what footprint that would require to start from some devices here and go to a different plane with perhaps a higher Q tank and that sort of thing. But if we could do that, then that would be helpful in terms of some of these equations that we have, where we have Q here. Beyond that, yes, if there are some devices that have lower flicker noise, that would be interesting. So for every oscillator topology, we have to go back and derive these equations, derive that alpha factor, and see how cooperative it is.
Well, thank you once again, Behzad. This has been a really great presentation. Really appreciate your time. Wish you and your family, continued health and safety, and also to everyone attending. Thanks for attending. Once again, all the best to you and your loved one's health. At this point, we'll return this back to Abira. Take care.
Thank you very much. Thank you.
Thank you, everyone, for attending the webinar. I put a few announcements in the chat. The webinar slides and video will be posted on the SSCS Resource Center by early next week. And I also posted a link to obtain a certificate of participation if you're interested. And please visit the SSCS website for information on upcoming webinars. We hold a webinar once a month, and we have an upcoming webinar hosted by our young professionals on Tuesday. Thank you.
Thank you. Bye.